Hello, my dear friends. Welcome again. Uh, this is Dr. Mohamed Nezami. Welcome again to my videos, my series of videos on KU band antenna to LNB feed structure design part two. If you recall, in part one, okay, and part one is already here. Okay, this is my YouTube channel. The videos are all in there. I would appreciate if you can please make sure you sign up to subscribe to the channel and share the videos. In part one, if you recall, we covered the principles of the LNB and the feed, the dual polarization feed for LNB through either circular or square waveguide. Okay, in conjunction, of course, with the rest of the system, be it phased array system or be it parabolic dish. And we did cover the septum principles, both the septum, circular polarizer, and the square polarizer. Today, and then we went into the dual polarization um, septum fed LNB, and we have detailed this in here, where we have a circular waveguide that is an extension of a horn antenna feed, right? This one here. The circular waveguide comes in here, and then the aperture, the facial of the circular waveguide in it is inserted a septum, which is just a stepped stairs of metal sheet. Okay, that basically what it does, this becomes your polarizer, septum polarizer, in which the circular propagated signal, the circular polarization signal, which is composed of either horizontal or vertical or both, extracted from the signal. And I have talked about how the septum works in conjunction with, in this case, of course, it's printed feeds. Now we could have, if you want, these can be also um, metal wire, basically, at feed as well, a probe. We showed a whole bunch of varieties of these. This is showing how the septum is inserted in the circular waveguide. The septum is extended outward to using a quarter wavelength, waveguide length that is shorted on this end so that the probe feeds in here sees open circuit on this side. As you know, a quarter wave transformer or transmission line, if it's loaded with short, it becomes open. If it's loaded with open, it becomes short. So what we do in this case, we short it so that the impedance looks open on the side, and you only see the loading from the both the halves of the septum polarizer. And this one acts also as a reflector, because what it does, all the waves that extend back will come back with a half wavelength phase shift because of the round trip of a quarter wavelength, which means they're going to come in phase with the signal and add up. Showed different varieties of these. I'm just going to skip through. You can watch the channel, the YouTube video, the part one, and see how that is done. And then we ended up saying, how do we design one of these? It's pretty simple. We take a printed circuit board and we make a cutout for the circular waveguide, and then we have traces in there for the probes, okay, printed. Of course, we have the middle partition, which is an extension of the last step in the septum polarizer, which isolates basically the two signals from each other. Now, realize in my case, which I'm going to show you, let's go to the file in the ANSYS HFSS. Um, this is the square uh, uh, waveguide. This is here. Okay, so realize that what I did in here is the cab, which is a quarter wavelength height. I did not make a cutout completely like you usually see in these, okay, in these boards. You can see that this board they hollowed out the whole thing except the cross that there is basically this is you can see the clearly where the septum is behind here, okay, and then this is part of the printed circuit board, and this is a cross, and they made just pies of cutouts in the board so that mechanically this will be stabilized, and then of course the cap in here, which is a quarter wavelength depth with the middle partition, comes in and closes this. And of course, you have little gaps on each side for the probe to come out to the LNA device. Now, in my case, I did not cut this out. And you can see that is in some cases they do that. So the board stays a whole intact, and the wave propagates through the substrate, which is in this case RO 4003. But on the other side, you can see I hollowed out the bottom side. It's the ground is not there. So I made the circle waveguide comes from the horn through the septum into the board aperture on here, and then it propagates to the other side of the board where the probes will pick up the signal. And of course, we can go back and show you that sometimes they don't hollow that out. Let me see if we can locate. Okay, here's one, for instance. You can see this was one, same technique. They didn't hollow the waveguide part. It has a little contribution, but it's negligible, so tiny. And in this case, of course, you can see it here too. So the probe in here, it was still, they just made a little bit of safety around the probe to cut out into the BCB, but it's still isolated completely. The same way is done here. And the same way is done here. So a lot of people, they cut it out completely. It does contribute a little bit, and I yet to show it in the modeling how much that is. Okay, so today we're going to go part 2, and we're going to continue. So now, what we have shown back here, all of these LNB feed assemblies, they use printed circuit board in conjunction with a septum. Printed circuit board probes in conjunction with a septum polarizer that is inserted inside the waveguide like you see here. And then, of course, you still have the back end short, which is the cab, which is the housing that encloses this, and also serves this cavity in here serves as an extension of the circular waveguide to back end short, okay, which is a quarter wavelength. Today, let's go into another lower cost technique, and that is basically using a without a septum first. We don't want to use a septum. We want to use a polarizer. It's not septum, but it's a very simplified septum, I would say. A single stage septum, a single stair septum. But it's using metal probes, okay, and a grid polarizer. And what that is basically, you can see here's the LNB complete with the horn in here and the circular waveguide in here. And these basically also, by the way, that fell on the floor. And let me pick that up. We can see that in here. Here's one. So basically, we have this is the board right here. Is basically housed inside, and here you have two probes that are orthogonal. And so what that is basically, as you can see it in this LNB in here, which is highly integrated using a mimic down converter chip. So basically, this solid ball here shows. This is where one of the probes actually is a wire probe that you can see here inside the circular waveguide on this side. You can see that right here. There is one probe and there's another probe, and they're perpendicular to each other. They're orthogonal. One is 90 degree offset from the other one at a distance, which is a quarter of a wavelength from each other. One picks the horizontal, one picks um, the vertical, but we need to have, of course, a quarter wavelength reflector on the back. Is the back end short? And so one of those physically, there is a short in the back of this circular waveguide that goes in here, while the other one, we use a single pole pin, basically. There's almost 3 times the size of the probe to act as a grid. They call it a grid polarizer, which all it does is, and it will be parallel to one of the probes, while it will be perpendicular to the other probe. And in a minute, I'll show you more details of this. And that's what you see basically here. This is a square waveguide with two LNB here, with two probes that you can see on the inside. And you see a third part, which is basically right in the middle of the waveguide that acts between the two probes at a quarter wavelength distance, that acts as a back-end short for that particular polarization. Okay. So we have one here, that's a pin right here. There's a probe that goes to the waveguide, okay? And there's another one, which is right here. And you can see they have a 90 degree from each other, because this one here in the middle of the waveguide, while this one on the side, but it falls off, it goes back to the waveguide and then it goes around. And I'll show you in a minute with a 90 degree, so that this becomes the horizontal, while this one is actually the vertical. So we've got horizontal polarized probe and circular probe, and I modeled them in the HFSS answers like this, okay? With in between them, exactly at a quarter wavelength, is basically where a single shorted to the body pole that is right in the middle of the waveguide that will act as a reflector or as a back short for this pin, okay? While this other pin, the horizontal one, we still have the back end of the waveguide to act as a back short to it. This is cheaper for high volume, and it's much better. It's cheaper to manufacture than this one here. So these are polarizer. These are LNBs that are like $5, each, because simply all they are is just the mimic ASIC or mimic RF chip in here that is doing the down conversion. We've got a 25 megahertz oscillator in here that will be the reference for the synthesizer, okay, inside this chip. And of course, you go through two-stage LNA amplification, and then the hairpin filter, which is the image rejection filter, and both of them feed this here, and we get two IFs in here. These are the two IFs, and this is voltage regulation. So let's focus more on this. How does this mechanism of feed assembly works? So this is a close-up view of a circle of a horn, corrugated horn, with a circular waveguide, and you can see clearly where we have the two probes and the grid pole. I call it grid pole. So it's right here. So basically, what we have one vertical polarization here that gets picked up, and a quarter wave distance from that first pole. Back here, we have what we call grid pole, or in essence, what it does, it acts as a back end short for this pole here, for the waves that are vertical polarized. And then we have another probe on the inside, which is perpendicular, orthogonal to this. And then, of course, what acts as in the back of that, this is away from the back end, which is by a quarter wavelength, another quarter wavelength. So we have a vertical pole, we have a quarter wave away into the waveguide, we have a pole that acts as a back reflector for the vertical wave, and then we have another 90-degree orthogonally placed probe for the horizontal, And in the back of that, we have a short, which is quarter wave. So we have one distance, which is quarter wave, quarter wave, quarter wave, three quarter waves from the first vertical probe. And you can see here is a close-up, another picture of this, another picture of this, another picture of this. You could also see it right into here, okay? You can see it right there. So you can see the inside of this where the three pedal pieces, and what they do, they feed the LNB, okay? Okay, so this is what the back of this board looks like, a board similar to this. So we have one probe which comes in like this, and then is bent 90 degrees. So this acts as a horizontal probe, which is also here, shown in here. And then we have another one which drops down in the middle of the waveguide, and that picks the vertical polarization, okay? So, of course, on the top side, this is the back. On the top side, all you see is, of course, where it's soldered. You see this solder ball here and this solder ball in here, that corresponding to here. So we have a clearance in the back ground plane of the board for those probes. Now, this probe in here comes inside the metal housing of the LNB. And what most manufacturers do is they put a sleeve, a Teflon sleeve in here so that this acts, this becomes actually a coaxial line. But in this case in here, theoretically, this you want it as a quarter wavelength, free space half wavelength in free space, the length of this. Actually, quarter wave, sorry. No, quarter wave. No, it's a half wavelength. I apologize. I'll show you in a minute what. Okay, here we go. So theoretically, these probes in here, okay, they act like really they are dual coaxial line to waveguide transitions. That's what they are, except they are embedded into the BC board. And the principle of this pole of the coaxial to waveguide transition basically says this, is that you get a waveguide, and longitudinally you place a pin that is a quarter of a wavelength. Here it is. So the answer is here. It's a quarter wavelength in free space, lambda 0, as you can see here, while it's placed away from the back short by a waveguide quarter wavelength, okay? And then, of course, the feed point is another quarter wavelength, okay? Now, the reflector in here, or the back end in here that acts, because the first probe, it's a half wavelength away from the back, the short back. So, but we need immediately a quarter wavelength away from the first probe to have a back short. And believe it or not, if you put a line in here like this, it acts as a back short. And the principle of this refers back to optics, is where you have, if you place lines, okay, and what happens if you have a signal that is multipolarized? So what happens is that really the lines in here will reject whatever polarization that is, whatever polarized wave that is perpendicular to this, and will pass through only the parallel ones, okay, parallel to the rod or to the pole. And that's what this does. So in case, so if you look at these probes in here, this one here is in between these two probes, two orthogonal probes, and it's a quarter wavelength away from each one of these. But it will act as a, so the signal in here, if it's vertically polarized, it will get picked up by this, and if anything passes past the first probe, it will actually reflect back from this pole that sits in the middle of the waveguide, reflect back to here. Same way as if you have completely shorted back waveguide. So here's another picture of this, actually. That's this guy here, okay, on the inside, okay? So as you can see, and here. So this is, if you were to assume this is the vertical, okay? And in this case, really, I swap these. This is the vertical, but in any case, it's irrelevant because you could rotate this anywhere you want as long as you keep track of which is which. So this pin in here picks up one polarization, and let's say it's a vertical, and the signals that passes through to the back, since this pole here is shorting the waveguide bottom to the top in the middle, and it's a quarter wave away from this pole, any vertical polarized signal will reflect off this. It will not pass through the square waveguide to the back. So only the horizontal will go to the back, and if it goes to, it will be picked by this line, this probe in here. And this probe in here, of course, any signal that doesn't get picked up and passes to the back, the back is a quarter wave away from that horizontal uh, uh, probe here. And what happened? It will reflect back in phase and sum up in here. And you can see the cutout in the waveguide wall is sort of like adjusted. It's a little bit much larger than it's a slit actually, not a hole for the pin. And that's because when you insert this board, you can see this. So you insert this board, you want to have a little flexibility in the way you insert this board. So you can't have just if it was a hole, it would get stuck in this 90-degree bend here in the horizontal probe. Okay, so basically the way this is modeled, so again, here is a horn, okay? And the circle waveguide is in the bottom of this, okay? And what happened is right about, I would say this distance in here, this circular waveguide is actually shorted. This is shorted here. It's closed in the back. So before that, by a quarter wavelength, waveguide length distance, we have one pin, which is this pin, the horizontal one. And then, of course, I'm sorry, this is the middle one, okay? And then we've got another one, of course, orthogonally placed about a half wavelength away from this one. So the distance between this guy and this guy is 3/4 of a wavelength, okay? And then in the middle here is where that is placed, that pole is placed. But that pole, between those two poles, the probes, it has nothing to do with the BC board in here. It's part of the bottom assembly where these two pins are. Now, just to show you how it's done in the HFSS model, let me show you. So this is the square wave guide one. So let's go. So here it is, what it is basically, and I yet to put the board in here. So the signal comes in on this side here, okay? And then what happened is we have a post that is shorting the waveguide, okay, top to bottom, that is parallel to this probe here. So all the signal that comes in here and gets absorbed picked up by this probe, if anything goes past, it will get reflected from here to here because this distance from here to here is a quarter wavelength. Now, while the other orthogonal polarization, it really doesn't see this probe and it doesn't see even this rod here. It goes back to this one here because it's orthogonal to this. So it goes to this probe in here, it gets picked up, and anything passes past that, it will come back again and get reflected back and get summed up because the distance between this probe here and this back in wall of the waveguide is short, okay? And just to show you how that is really working, let's go to the, and this is still needs to be optimized, but we can see, let's show here, let's animate this. So here we are. You can see now the signal. If you look from top, you can see which way is this. Is this right hand or left hand polarized? So we go to the top. you can see that it's counterclockwise. So it's going to the left side. So this is a left hand polarized signal. And what you can see is that part of the signal gets picked up by this probe and part gets picked up by this. And of course, the middle in here, you can see the middle where that rod is. Let me that grid polarizer. Let me just show you where that is. Okay, I think I made this copper. Let's see. So this is the feed in here. Okay. Short. Okay, here it is. So I just picked that up so I can show where that is. You can see that this is right here. One of the polarization doesn't go past this guy here. It sees short waveguide, just like this probe here sees back there. So let me show the probe. Okay, which way is the probe? Okay, this is the end. So, okay, here it is. That probe right there. Now, let's say I want to pick up the signal right-hand sided. Okay, if you go right-hand sided, you can go over here and change your the face on the on one of the E fields of the. So let's go here. So I'm going to make this 0 degrees and this 90 again, and watch the polarization switch from left-hand sided to right-hand sided. And of course, this will be swapped as well. The signal will go, okay, there you go. See? Now we have a signal going the other directions, okay? And now this is really working perfect, because what this guy here is picking half of the signal, while this guy in here is picking half of that signal. Of course, now the signal itself is what's being fed to this from this end. Let me show you here. This is the common part. So I'm basically feeding the signal from here. This signal has two independent modulated signals, because just like in TV, you have on SATCOM TVs, you have vertical polarized channel and horizontal polarized channel, and they're totally separate, different, even though they're at the same frequency, but they're totally different programming. So, and of course, that's really what happens is that the signal, when I explain this to students, a lot of and my trainees in this workshop, they think you lose 3 dB. You don't lose 3 dB. Yes, if you assume that the signal in here, the vertical and horizontal, the vertical gets completely picked up by this, while the horizontal gets completely picked by this. So really, you have the whole signal except the feed loss in here. Okay. So again, what this is, and we'll go in the next parts, we will go through more on this theory. So really what happens is, so one polarization gets picked up by this, one polarization gets picked by this, and of course then both of them, like you would see on this board in here, here's one pin on this is the top side, looking at the board on the top side, and here's another one. So you go through a two-stage amplifier and then an image rejection filter and into the mimic down converter chip, where the other polarization comes in here, goes in and goes into this second one in here, goes into this, the same chip. So this chip here is really doing simultaneous vertical and horizontal down conversion, of course. Okay. Now, in some of the LNBs, like I showed way back when we introduced this concept, some of these LNBs doesn't give you both simultaneously. They just basically, they switch on off the power to either the horizontal LNA or the vertical LNA. And then you only get one or the other one, okay? And switch back and forth between them. While other ones is where you get the vertical and horizontal are always present, but two different IFs. Now, some designers and some LNBs, they have a single IF, but what they do is they have a local oscillator that is different. They're offsetted from each other, for both polarization, and they end up chopping the band and lining them up right by each other, okay, so that they can use a single IF. Okay, so let's get back to here. Okay, so now we know the principle of this, how it works. Okay, so basically this is the modeling, and these are the two pins on the bottom of the board, the LNB board. Okay, well, okay, now just like you would think that somebody said, I want both. So we have some LNBs that gets fed by probes like this, wire probes, and some that we saw that are fed like these in here. But you need a polarizer. In this case, in here, we didn't need a full polarizer, but we needed a back-end short to one of the polarization between the two probes, and we do that by a single grid of wire, and so installed inside so somebody came in and says, well, why don't I have both? Okay, and that's exactly what we have next, is we have a mix, some LNB feed assemblies. They utilize both the orthogonal probes. One of them will be printed while the other one will be metal pin. Okay, and that's exactly what you see in here. So here's one LNB. This is a dual side LNB with dual feed. Okay, and so you can see one printed one here, and same thing printed in here, but also on the bottom of this board has another orthogonal pen, wire pen, that is orthogonal to this printed pen, and it's exactly at a quarter wavelength away from this one. Now you might think, okay, so in theory it's just like this, except one of them is printed. But what about the short, back end short to the first pen or the first probe? Well, that they took care of it, and what they do, of course, is in the middle in here. You can see that on the back of the board. Look at this. They printed a short trace, a trace short to the ground. And of course, the board itself is cleared of copper to let the signal propagate through on the circular waveguide. So this comes in right here. So the distance away from here, this distance, vertical distance in here, away from the board itself is a quarter wavelength, okay? So now we have this pin in here, okay? And in the back of that, we have a, basically, the board is clear, except we have a short for at this guy in here. So where is the short back end for this guy in here? Well, it is the lead that comes in here. I didn't put it in here, but it's a housing that comes in here, and the housing height above this face at the top of the board will have a height of quarter wavelength away from this printed probe, while the other probe is actually the back end short is this one here. It's also printed, okay? And you can see it here. Here it is. And in this interesting one in here, because you can see there's a little sleeve of Teflon, so that when this pin in here gets inserted into the housing of the LNB, this one here will act as a coaxial waveguide. So they want to reduce the loss. So you can see clearly now, honestly, that one of the polarizations will always have worse noise figure than the other one, which is this one in here. I would doubt, and I will see it in the if I get to model this in one of the coming sessions. This one in here has much less loss than this would, because this has to go through a through hole and then a sleeve of a and then a bent in the wire, the probe itself, to get into the waveguide. Okay, here's another picture of this. So we can see that this is coming in here, this one probe. Here's the cover, which acts as a back-end short for this. Now, while on the other side, we have, of course, another probe, which is this one in here. And of course, this piece in here is acting as a short back end to that one. The same thing we got here, same exact thing, except in here they put a little bit of copper to extend the length of, to tune the length of this. Okay, so ladies and gentlemen, so we've got three types of LNB feed assemblies. One of them, we saw that it's the one that basically we saw back here. So basically we have a polar, or let's go back here. We have a septum polarizer inside a waveguide that feeds the LNB board. And then we have the back end is basically a cap that covers this. And we have printed two probes that picks up the vertical and horizontal. That's one. And then the other one that we have is the dual polarization circular square waveguide LNB feed using metal orthogonal probes and a grid polarizer. And that's really these ones in here. That we saw that in these ones, what we do is we have the horn, and then we have a board that sits on top of the horn. One of the probes drops down right in of the board into the waveguide and picks up the vertical horizontal polarization, while quite a wavelength away from this probe in here, we've got inside the waveguide, there is a fixed pole that is basically physically connected or soldered from top to bottom, acting as a back short for this probe because it's in parallel to the wave. And then of course the same board, we've got another pin that comes in orthogonal to the one that drops from the ceiling of the circular waveguide. And of course, these from each other, they're quite a wavelength away from each other, okay? And I'm sorry, these are a half wavelength away from each other. In the middle, because in the middle, we have this guy here, the back and short implemented by the grid, the pole in here, okay? All right, and then the third one is this case here, where we have in one case we have the horizontal, we have a wire pin implementing the probe, while the other polarization, the vertical, is being picked up by the printed probe and then goes into the LNA section. So these are three, and we want to investigate all these three types in the coming sessions. So in order to do that, I have created a circular waveguide section, put a septum inside of it, tested it, and then put the same one in here, attached coaxial lines just to make sure that it works, okay? And then for both the circular waveguide and the square waveguide. So we do that for the square waveguide. And then, of course, we have the LNB assembly feed that is done with two pin probes, just like we do here, okay? And then, of course, we have developed the full-blown version of the dual printed pole assembly feed that is here, like this, printed, completely printed with a cap, okay? And then we have the same thing for a square, okay? And of course, next is we want to create a board that will replace these coaxial transitions in here. There'll be a board in here that will pick one polarization here and the other one in here using a 90-degree bent pen from the outside. So there'll be a board on top of this. And that's basically what we need to. And then, of course, the third case is this here, where we will keep this one here. But on this one here, we'll replace it with a printed probe, okay? So, and that's really what we see here, what I did here, okay? So we can see that this is what we're going to do is we're going to come back to this. So we've got the circular waveguide is done here. We study the mode of the circular waveguide, like for instance, in this case, we look at the modes propagating through this just to make sure that the distance, that we have a clear area between the next lower mode is enough so that we can operate. And in this case, we're going from 10 gigahertz to like 12 and a half gigahertz, and we can see that we're really good. This is 18. The diameter is 18 millimeter, of course, for this one in here. Okay, so we study this, and then we look at the return loss is good at the lowest mode. We look at the cutoff frequencies, and again, like we said, we see that the lowest two order modes are away from each other so that we can operate the LNB. And then we look at the, of course, the impedance on this. And then we can actually view the the electromagnetic signal inside of this, and we can see it right here for circular polarized signal. So let's animate this. Or before we do that, now you can see that, as you can see, the TE11 mode, and let's see, we can see that the modes, you can see that, we go into the lowest mode, and the second one, a third one, fourth one, fifth one. Okay, these are all the different ones, and we can. Of course, we're trying to operate the middle band is 11 gigahertz, and I did a computation for the wavelength. The wavelength is almost 59.3 millimeter. Okay, so we could measure that and make sure that that is the case. Let me show you how we measure that. And if you go to here, let's put this like this. Now you can see the pattern, the E-field pattern repeats every half wavelength. So you can come in here and you can measure, for instance, the position from this point to another similar point to that. And you can see right there is about 28 millimeters. 28 millimeters, and we did compute the wavelength for this is around 59.3. Half of that is 28, so something. And we're not exactly accurate, but we can become more accurate if you want. Or you could measure it from the highest field in here to the highest point in here, and you can see it's 28 again in there. Okay, so now we can see that we can stimulate this with a signal. Let's just emulate the animated. Okay, so you can see that the signal rotates right now is clockwise. Okay, so it's a right-hand wave circular polarized signal. If I want to reverse that direction, you just basically go out and introduce the 90-degree phase shift instead of being to the vertical one to the horizontal one. And that we can do right now and show you quickly. We can put that 0. This is 90 here. And then, of course, you can put any angle. It doesn't have to be 90 degrees. So you can actually have sort of like an elliptic. You can create an elliptic. And you can see that it did switch directions. If you missed that, let me go undo this. And you can see that it will rotate the other way around. Okay? Redo it. And you can see that it's doing this. Okay, so we're going to go do that. And then, of course, we're going to do the same thing to a square wave guide. Before we do that here, so in any case, and then we're going to insert all of this. So basically, what we're really doing is we're going to introduce this whole family of things that we do here. I'm going to go in the next sessions. We're going to go through these and show you how to design both of these. Now, I have my every 3 months I hold a 1 week training shop that I would like to. In the next video, I will put the information out so that if you like to become a trainee and come to this training that is 1 week where basically you get a copy of all these simulation files and you get to do them. So we do them in class. So we introduce a theory, all the mathematics we do, and then you sit down on the HFSS, ANSYS HFSS, and do this, or on the ADS for the active portions. Okay, ladies and gentlemen, so Now, I would like to thank you again. So we're looking forward to see you in the third part of this. So until then, have a great day, night, whatever it is where you are. Thank you very much.